So Stokes' law is just an observation and finding a relation between how objects move inside a fluid. Raindrop which is coming down under the influence of gravity, gravitational force is acting downwards. But again there is one more force which is acting upwards. The property of a liquid by which its surface behaves like a stretched out elastic membrane is known as surface tension. Pressure inside the liquid droplet is greater than pressure outside the liquid drop. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about some fluid mechanics. So let's see what fluid mechanics actually holds for us today. So Stokes' law. What exactly is Stokes' law? It just dictates that, again, if we have a beaker full of fluid, let's imagine that we have a beaker that is filled with fluid. Now, what happens if I drop a metal sphere inside that particular fluid? Right, you will imagine like pluck, and then water will splash out. That is if you're imagining water. What if you're imagining a big beaker of honey? Will that pluck be still there? No, right, that pluck won't be still there. So again, that pluck and the way that the liquid actually moves, or simply the fluid actually moves, is because of certain properties that particular fluid has, and that is linked with this particular law, that is Stokes' law. So Stokes' law is just an observation and finding a relation between how objects move inside a fluid. So for example, we can say that in this particular case, a metal sphere is dropped inside a beaker which is containing fluid. So what is happening to that particular fluid? So it was observed that this particular velocity of this particular spherical ball, that is the velocity at which it is moving through the fluid, is directly proportional to its viscous force, and it is also directly proportional to the radius of that particular sphere. So how is that particular thing related mathematically? That is what is Stokes' law. So what Stokes' law states is that the viscous force on a sphere is directly proportional to the velocity and radius of the sphere and viscosity of the fluid. So again, viscosity determines how a fluid can actually flow. If the viscosity is really high, the fluid can flow only by a little margin. But if the viscosity is really low, which means the fluid can flow very easily. For example, honey is a highly viscous fluid, while water is a very less viscous fluid. That is compared to honey. And if you compare air with that, air is even less viscous. So that is what viscosity or just viscous force actually means. It's just a measure of how thick that particular fluid is, or how easily that particular fluid can flow. That particular concept is related to viscosity. And again, that is directly proportional to the velocity of the sphere. That is, if this particular liquid or fluid is very viscous, then this particular sphere will have a very rough time traveling through that particular viscous fluid, right? If it was air, it will move very easily. If it was water, slightly less easier. And if it is honey, it is going to be very difficult for it to move. That is, to attain a high velocity, it will be very difficult for that to happen, even though gravity is pulling down on it. So again, this particular viscous force is indicated by Fv, meaning viscous force, equal to 6 pi eta Rv. You don't have to worry about the derivation, how this came into effect. All this you don't have. You just have this particular equation and this law to be understood. And again, this is coming from the equation, that is Fv is directly proportional to Rv. And here, this is a constant value for a given fluid. 6 pi is already a constant because 6 is a number, pi is a number. And eta is known as the coefficient of viscosity. So eta is known as, this is eta. Eta is a Greek letter which is symbolizing or just specifying viscosity of a fluid. Coefficient of viscosity, how viscous that particular fluid is specified by this particular quantity which is known as coefficient of viscosity. So again, when a sphere of radius r is falling downwards like this, the viscous force will be acting upwards like this. It will be preventing the sphere from entering into the liquid, moving it aside and going deeper into the liquid. So that particular concept, how it is affecting that particular liquid, or simply how the parameters of the sphere is affecting the viscous liquid, is laid out by Stokes' law. The next topic is terminal velocity. What exactly is terminal velocity? So what is terminal? Terminal means that it is the last point. So is it the last velocity you can attain? Not really, but actually it is. So the problem is that if there is a big cloud and there is raindrops coming from that particular cloud, we assume that in the problems, we assume that, okay, the raindrops are falling under the influence of gravity alone, which means that no other forces are in play. That is just to make the equations and the problem much more easier for you. But in the actual real life situation, that is not the case. There is air resistance, there is buoyant forces, there are a lot of forces in play which we are not considering when we are solving certain physics problems. Because the first thing you see is that neglect air resistance. Neglect air resistance. And then you start to do the problems. But there is a catch. If you neglect air resistance, then what happens to the velocity of this particular raindrop? We know that acceleration due to gravity, that is g, is equal to 9.81 meter per second square. Let's just approximate that to 10 meter per second square. Okay, so if that particular raindrop is accelerating 10 meter per second, that is, it is accelerating 10 meter per second square every second, then what will be the velocity of that particular raindrop? It will be coming down like a bullet. It will be coming down like a bullet onto us. And most of the life wouldn't survive. If there is a leaf or a tree in the way, it will just puncture the leaves and go right down into the ground like needles. But that is not the case. If we are traveling in the rain, if you love to walk in the rain, that is only because the velocity is not increasing 10 meter per second, 20 meter per second, 30 meter per second like that. Because if that was the case, each meter, the velocity would go 10, 20, 30, 40, 50 like that. And by the time it reaches you, it will be like 200, 300, 2000, 3000 meter per second. That is too much. But in actual cases, raindrops are not that much stingy, but slightly, but not that much like a bullet. That is because even though they are accelerating initially, they slow down and attain a constant velocity. Instead of increasing its velocity at every second, it is attaining a constant velocity after some time. So why is this constant velocity attained? That is because of the various forces that is acting on this particular raindrop. Because when the raindrop is coming, air resistance is pulling it up, right? So we are just saying it air resistance. There are specific forces which are in play, but let's assume that air resistance is preventing the raindrop from attaining the harsh velocities which I just talked about. Which means that because of the air resistance, a force is acting upwards. Okay, just assume that there is a force acting upwards, which means the raindrop which is coming down under the influence of gravity, gravitational force is acting downwards, but again there is one more force which is acting upwards. And this means two forces are in play and they are in opposite directions. If two forces are in play and they are in opposite directions, obviously they will add together and the resultant will be a smaller force, whichever force is dominating in that particular direction. So we can say that even though the raindrop is coming down under the influence of gravity because of certain forces which are there, it attains a constant velocity, which means the forces are cancelled. On a raindrop, we can say that the force coming down and the force going up are equal, which means the net force is 0. Because there is no force, the raindrop cannot generate acceleration, because in the absence of force, there is no acceleration. Hence, we can say that raindrops have constant velocity after some time. So again, what is this constant velocity? This particular constant velocity itself is known as terminal velocity. That is, initially the raindrop will be accelerating, but after some time it will attain a constant stable velocity because of the forces balancing out. This particular velocity is known as terminal velocity. So again, we can define terminal velocity as the maximum velocity at which net force on a falling body becomes 0. So again, if we take the example of a raindrop or any other material which is falling under the influence of gravity, we can say that if any object is falling under the influence of gravity, after some time it attains a constant velocity, and that particular maximum velocity is known as terminal velocity. And why it happens is because the forces are balanced out. So again, if any object is falling, it is because it is under the influence of gravity. So the force acting in the downwards direction is gravitational force. So again, what is balancing out that particular force? Since it is falling in air or simply a mixture of gases, we can say that it is traveling through a fluid medium, which means the fluid medium will exert a pressure. We just saw that using Stokes' law. So we can see that there will be fluid pressure, which is Fv, acting in the opposite direction. And there is one more force that is known as buoyant force. You have already studied this in your high school syllabus, that is buoyant force. So again, if anything is immersed in your high school, you studied it as liquids. That is, if anything is immersed in a liquid, it displaces equal amounts of water and the object feels an upward force which is known as buoyant force. So it is not just for liquids, it is also true for fluids. So we can say that Fv is viscous force and Fb is buoyant force. So these two forces, that is, these two forces combined will balance out this particular gravitational force. So we can just say that Fg will be equal to Fv plus Fb. Okay, because these two forces are equal, they cancel each other out, and then we can attain terminal velocity. But we already know an equation for Fg. That is, if any mass is falling under the influence of gravity alone, we can just say that it is m times g, right? That is gravitational force, which is equal to Fv. Fv we just learned, that is 6 pi eta Rv. So this is 6 pi eta Rv. So again, Fb, since it is a new force for you, just keep it like that. I'll tell you what is the value of Fb is. It is actually the same value as mg, but again, just keep it just like that. It'll be the same value as one of these quantities here. Since it is a new force for you, you don't have to learn it from the scratch. Just understand this particular derivation. That will be enough. So again, we started with this particular equation, but we know that Fg is nothing but mg, mass times acceleration due to gravity, and we also know that Fv, that is viscous force, is 6 pi eta Rv. We wrote it down, and here the problem is that we saw mass in fluid dynamics. So whenever we see an equation in terms of mass in fluid dynamics, we convert it in the terms of density. So we can just say that m will become rho v. So we can rewrite this as Fb a plus 6 pi eta RV is equal to rho V into G. There is a V here, there is a V here. Don't go ahead and cancel that particular V because we have a slight use for that. So keep it just like that. So again, now I'll tell you what FB actually is. So FB is actually having the same value as that of this particular rho Vg. The only difference is that this is because of the body and this particular force is because of the fluid medium. So we can say that this also is rho Vg, but the only difference is that it is rho FVG, that is because of the fluid medium, and this is because of the body itself. So 6 pi eta RV is equal to rho BVG. And again, you couldn't cancel out these V's because there was a plus sign here. Even I forgot that. So don't make that particular silly mistake. Just because you see two V's, don't cancel it out directly from there itself. And again, remember rho F is the density of fluid and rho B is the density of the body. Remember, one is density of the body and the other one is density of the fluid medium. So don't confuse this rho F and rho B. They are different quantities. Now I'll do one more thing, that is arrange all the rho V terms on one side and take the silly looking term onto the other side. Then I can write it as rho B Vg minus rho F Vg is equal to 6 pi eta RV. So again, we have some common terms here, that is Vg and Vg. So we'll take it right outside and we'll say that rho B minus rho F into Vg is equal to 6 pi eta RV. So now we can definitely cancel out the V and V, right? Please don't cancel it out because one is in terms of velocity while the other V is in terms of volume. So this small v is in terms of velocity and the large V is in terms of volume, because again density times volume is what? Mass, right? So again, but here in this particular equation it is velocity. So the both, even though both terms are indicated by V, it is one velocity and the other one is volume. Why that happened? Blame physics because both had starting letters V. So again, this particular equation we arrive at. Now we can evolve this particular equation. That is, this particular V is volume. So we are going to substitute the equation for volume, that is rho B minus rho F into volume, that is 4 by 3 pi R cube. 4 by 3 pi R cube. So again, 4 by 3 pi R cube is the volume of a sphere. We are assuming that the liquid drop that is coming down from hailing from the skies is perfectly spherical drop. So that particular drop will have a volume of 4 by 3 pi R cube, and there will be a G here which will be equal to 6 pi eta RV. Now cancel all the terms you want. That is, there is an R and R here, which means this will become R square. There is a pi and pi here, which will also go away. Now we can just make a few rearrangements and we have our equation. So in this side there is only 6 eta V, and in this side there is only rho B minus rho F times 4 by 3 G. So rearranging this particular equation, we'll have an expression for velocity. So V will be equal to 2R square G divided by 9 eta into rho B minus rho F. So again, rearranging this particular equation, you will get it as V is equal to 2R square G by 9 eta times rho B minus rho F. So again, how? Just keep the V here, take the eta to this side. So this will go to the denominator. This also will go to the denominator. So 6 times 3 is 18. So 4 by 18 is 2 by 9. So again, if you bring the 6 to this side, then you will have 6 into 3. You can cancel this and the 6. That is 2 by 3. 2 by 3 meaning 3 into 3, 9. So that is why 2 by 9 is here. Then again, so there is an r square here. This r square is here. So again, 2 by 9 r square g into rho b minus rho f. That is this particular equation. That is, this is the equation in order to find what is the terminal velocity of any object. So the next topic is again very simple because you have already studied it in your high school syllabus. That is, if you have a beaker of water and if you drop very carefully a steel blade or iron blade on top of this particular surface, then it actually floats. You can see water sticking onto it and it floats. Or if you drop a leaf also, it floats. So the leaf is less denser than the water. Again, leaf density, look for some other reasons. There are other phenomena. Because if this was a lake, you can see water striders, that is small aquatic creatures or small insects which run over the water, water striders, water spiders, and small other insects also, which glide through the water. They don't break and swim inside the water. They just glide or run around the water. Is it because these creatures are divine? No. Not because Jesus blessed water striders with anything. No. Because of certain physical properties, they are able to do this. So what is that particular physical property? Again, you have studied this in your high school, that is surface tension. The property of a liquid by which its surface behaves like a stretched out elastic membrane is known as surface tension. Or much more simply, we can say that any liquid will try to reduce its surface area and to reduce its surface energy to a maximum, which means that it will try to pull in. If you drop tiny little drop of water on a table, you will observe that it is in this particular shape. Why is it in this particular shape? Why is it in a spherical shape? Again, this is flat because it is being dropped on a table. Drop of water in mid-air, it will form a perfect sphere. So again, why is it forming a sphere? That is because liquids have a tendency to reduce, anything in the universe have a tendency to reduce its energy state. So in order to reduce this particular energy state and in order to have minimum surface area, because surface area increases, surface energy also increases. So in order to reduce that particular surface area, surface energy, the most efficient shape is a circle, or simply in 3 dimensions, it will be a sphere. So if it is a sphere, it means that all the molecules on the surface of that particular liquid drop is trying to pull itself inwards towards the bulk of the liquid. When it is trying to pull itself in towards the bulk of the liquid, the surface behave like a stretched out elastic membrane. This particular property is known as surface tension. So again, mathematically, we can say that the surface tension is nothing but that is the force applied per unit length. Again, if you have a liquid drop like this, force will be applied and that measured per unit length will be known as surface tension. That is mathematically. Or physically, you can just say that surface tension of a liquid is the property of a liquid surface to minimize the surface area of that particular liquid drop. So that is known as surface tension. Now, why did I just discuss about surface tension? Because in your high school syllabus, you have already learned about how adhesion and cohesion works. That is, attraction between same kind of molecules and different types of molecules. Attraction between same kind of molecules meaning, if two water droplets are nearby each other, they will attract each other and form a bigger water droplet. What is attraction between different types of molecules? Well, if you have a piece of paper and super glue, then you can see that you can stick various types of things onto that particular material, or simply attraction between different types of molecules. So simply we can just say that the attraction between different types of molecules is known as adhesive forces of attraction, and attraction between same type of molecules is known as cohesive forces of attraction. That is not what we are here to study about. So because of this particular weird force of attraction between different types of molecules, the water or any liquid you take inside a tube has a tendency to either stick to itself or to the walls of the container, depending on which force is dominating. Is it adhesive forces or is it cohesive forces? For water, the cohesive forces are not dominating and the adhesive forces are dominating, which means water will stick on to the sides. If you take your pen, open the refill and look very closely, you can see that there is a tiny little curve like this. That is because adhesive forces are dominating. The water molecules are sticking to the walls of the container. It is sticking to the walls of the container. That is why it is slightly appear to be raised. Okay, and if you take any other liquid, let's say any other liquid like mercury, then cohesive forces are dominating. So if you have ever observed a mercury thermometer, the N will be like this, because the cohesive forces are dominating. The liquid is trying to stick to itself. Mercury does not stick to other metals very easily, meaning other surfaces very easily. It will just run over other surfaces. It has a tendency to stick to itself. So the cohesive forces are dominating for mercury, while adhesive forces are dominating for many other liquids like water. Now again, what is all this related to contact angle? So again, I just told you that water seems to stick onto the walls of the container. The way it sticks onto the walls of the container actually is at a particular angle. And this particular angle at which this particular sticking of various liquids happen onto the walls of the container, that particular angle made is known as angle of contact, or simply contact angle. That is what we are going to learn in this particular small session. So it is mathematically described as the angle between the tangent to the liquid surface and the tangent to the solid surface. So it means that when the liquid is making contact here, just touching the liquid, I'll draw a tangent. And just touching the solid surface also, I'll draw a tangent. Okay, I made this gap so that you can understand there is one tangent coming here. It will be along the solid surface. So the angle between these two tangents will be known as the angle of contact, or simply the contact angle for that particular liquid. So again, remember, if surface tension is more, the contact angle will be more. If surface tension is less, the contact angle will be less. Because again, it will behave like a stretched out elastic membrane, making it stretch even more, increasing the angle, or if the surface tension is less, it decreases the angle. So that is all about contact angle. Now, why did we study about contact angle, surface tension and all those things? It is to just know what is excess pressure inside and outside certain things. For example, have you seen grass in the morning? In the very cold mornings, actually, you can actually see one liquid drop under a grass leaf. Simply under the leaves of grass, or like a blade of a grass or leaves of any other plant. If it's a very cold morning, you can actually see a liquid drop under this particular leaf. That is known as a dew. So you can actually observe dews under leaves. So why does dews under leaves appear? That is because of condensation. I'm not going to interfere in that. It is completely left to your biology, chemistry and lower grade physics things. But here we are going to talk about what is the pressure inside and outside that particular drop of water. So again, we are going to discuss this for a liquid drop. So what is the excess pressure inside a liquid drop? So again, where will be the pressure more? Inside or outside? Again, imagine if this pressure is more, what will happen? The drop will compress and collapse on itself. So which means the pressure is not heavy on the outside or larger on the outside, but rather it is more in the inside. So we can say that pressure inside the liquid droplet is greater than pressure outside the liquid drop. And you don't have to study how we derive this particular equation for pressure inside a liquid drop, but rather you have a pressure inside a bubble, that is inside a liquid bubble. So you don't have to study, you don't have to study the derivation for this particular excess pressure inside a liquid drop, but you have to know what is the excess pressure inside a liquid drop. So it actually depends on the radius of that particular liquid drop also. If the radius is very large, the pressure will slightly be less. That is, the difference in pressure will be, that is Pi minus Po will be comparatively less if the radius of the liquid bubble or simply the liquid drop is too much. So we can see that excess pressure indicated by delta P, that is Pi minus Po, will be equal to 2 times the surface tension divided by the radius of the liquid drop. Here remember, S is the surface tension of that particular liquid, because now it is water, maybe tomorrow it's honey, day after it's blood, maybe some other liquid, we don't know. So depending on the liquid, the surface tension value actually changes. So that is why S is there. So 2 times the surface tension divided by the radius of that particular liquid droplet will give you the excess pressure inside, or simply the excess pressure of a liquid droplet. So you can't do this, you can't say that the liquid drop will have this much pressure, we don't understand this. Okay, we'll do one thing, we'll solve it for a bubble which is having a liquid surface, but inside and outside it is air. So again the same assumptions, that is, there is a bubble. Again, imagine a simple bubble, a soap bubble which you made just out of soap things, or like you have a bubble blower, right? So you made a big bubble like that. So you have a bubble in which again Pi is the pressure inside and Po is the pressure outside. So again R is the radius of that particular bubble. So what I did is that I just gently inserted a straw inside and just blew inside that, so that the radius of the bubble increased very slightly, very small. That is, if this was the initial radius, I made a small enough pressure inside the bubble so that the radius increased by a factor of delta R. Delta R is again very small. I just did a very small work inside that particular bubble or on that particular bubble, so that it just expanded very slightly. Okay, so if it expanded very slightly, I can just say that the area actually changed. It means that AF minus AI. That is, the change in area will be equal to final area minus initial area. So the final area we have to find out, initial area we have to find out, because we already know what is the equation for area of a sphere. Again, area of a sphere is equal to 4 pi r square. 4 pi r square is the area of the sphere. So this will be the initial area. The final area will be 4 pi r plus delta r whole square, right? Because the radius is now r plus delta r. So the final area will be 4 pi r plus delta r whole square, and then the initial area will be 4 pi r square, right? So we can directly find out what is the change in area, that is 4 pi r plus delta r whole squared minus 4 pi r square. So again, what is r plus delta r whole square? So a plus b whole squared is equal to a square plus 2ab plus b square. Same formula you can apply here, and then you will get it as 4 pi r square plus delta r square plus 2r delta r minus 4 pi r square, right? So again, if you square this particular quantity, we will get this particular result. So again, we are going to take a small assumption that since delta r is already very small, delta r square will be even smaller than that. Imagine if delta r, that is the increase in radius, is 0.001 units. If I square that, again it will be even smaller than that. For example, 0.0025 units. If I square that, it will be even more smaller than that. So since it is getting smaller and smaller, we are approximating, that is, since delta r is very small, we are approximating that delta r square will be approximately equal to 0, which means this equation can be written down as 4 pi r square plus 2r delta r is minus 4 pi r square, which is equal to the change in area. So again, here if I open the bracket, there is a plus 4 pi r square and minus 4 pi r square. That will cancel each other out, and the only thing that will be remaining is 4 pi into 2r delta r. So again, delta a will be equal to, if I open this, this will be 8 pi r delta r. So this will be the change in area. Now, since we have the change in area, now we can begin our actual derivation. That is, when I blew inside the bubble and made it a little bit bigger, I did an actual work on that particular bubble. That particular work can be found out using the equation F dot S, or simply F times S. So here, since I am talking in terms of pressure, I'll write this particular force in terms of pressure only. That is, force is equal to P times A, because P is equal to F by A. From that particular relation, you can arrive at force is equal to pressure times area. So again, pressure times area. So pressure times area times the displacement. Here the displacement just means that the bubble expanded. So that particular small expansion is the displacement, and that is indicated by delta r. So we can just say that it is equal to P times A times delta r. We already have an equation in terms of area, and we already have an equation in terms of pressure. Pressure is just delta P, that is excess pressure, pressure inside minus pressure outside. So again here, this particular pressure is the change in pressure, which is indicated by Pi minus Po. And area we already know, that is nothing but 4 pi r square into delta r. So we have this particular equation right here. And since Pi minus Po is nothing but delta P, we can say that W is equal to delta P 4 pi r square delta R. Now this particular work done is stored as its potential energy, or simply in this particular case it is stored as the surface energy. So this particular work is actually equal to its potential energy, or simply in this case it is surface energy. So this work is stored as its surface energy of that particular bubble. So when I do a work onto that bubble, the work is converted into surface energy of that particular bubble. So again, one more meaning is that if I can define surface energy like this, then I can also say that surface tension, which is defined as force per unit length, also be defined as the surface energy per unit area. So surface energy per unit area, delta U by delta A. Again, you know what is delta U. So again, substitute that. S will be equal to delta P 4 pi r square delta R divided by delta A. Delta A is already found out, that is 8 pi r delta R. So you can cancel out all the similar terms, that is delta R and delta R, R square and R, pi and pi, 4 and 8, which means the only thing that will be remaining is delta P by 2. There will be an R here. If I rearrange this particular equation, I can say that excess pressure inside a bubble will be equal to 2S divided by R. So there you go, the derivation in terms of a small bubble. So later you might be sad, you might not be sad, but you might be sad that I didn't do the derivation. But if I do the derivation, this is how the excess pressure equation will come out for a bubble. So I hope you have understood how a bubble has excess pressure. So the next topic is capillary rise. Again, you have already studied what capillary rise is in biology and in physics and in chemistry. So again, capillary rise just means that it is the rise or fall of a liquid along very narrow and constricted tubes. Or simply, along very narrow tubes, liquids tend to rise or fall, and this happens because of surface tension, and this particular property is known as capillary action, and there can be two actions, that is either rise or fall. Depending on that, we say that it is capillary rise or capillary fall. So the phenomenon by which a liquid rises or falls through a thin tube dipped in a liquid is known as capillary action, and that is responsible for capillary rise. So surface tension is responsible for this particular phenomena, that is capillary action is only possible because of surface tension. So why did we just discuss this? Because we have a derivation in order to find how this capillary action, or simply capillary rise, actually happens. So let's see the mathematical truth behind capillary action. So again, I'll consider a situation where I have a beaker full of water and I've inserted a very small tube. Again, remember, I've enlarged this so that you can understand the derivation. So a very small tube is immersed in this particular liquid, which means the liquid will rise up slightly, that is capillary rise, and it will stick onto the walls of the container. So again, I'll take three different points, that is point 1 at the level of this particular water surface, at point 2 which is slightly just below the surface of the water inside the tube, and a point just above that particular water surface, that is P3 is the atmospheric pressure, and again P1 also will be equal to the atmospheric pressure. Why? Because liquids at same level will have same pressure, the hydrostatic paradox. I have discussed that. So we know that P1 will be equal to PO. PO is simply the pressure which is outside that particular beaker. And P3 is already outside, which means that P3 also is equal to PO, which is pressure outside. And again we know that we know an equation in order to find the pressure difference. If we have a liquid that is having 2 points and we want to find the pressure at the 2 points, we already have an equation for that. That is P1 is equal to P2 plus the factors affecting pressure, that is height, density and acceleration due to gravity, that is h, rho and g. In this particular case, we know that P1 is equal to PO, so we just write it as P2 plus h rho g. So this is equation number 1. Now, from here I am going to assume something. See this particular shape, this particular dip shape is almost like it is resembling a bubble. Some big bubble is sitting on top of that particular fluid. It is resembling like that. So I am going to assume that this is like a bubble which is having a radius of r, sitting on top of that particular surface. So I can simply say that it is very much like a bubble, which means that the pressure of the bubble will be higher than the pressure just outside. We just proved that. So if I imagine that surface to be a bubble, just for mathematical sakes, I can say that the pressure inside this bubble will be higher than the pressure outside, which means I can formulate an equation in terms of excess pressure that can be written down as delta P, which is equal to pressure inside minus pressure outside, which in this particular case is P3 minus P2. P3 minus P2. And again, P3 minus P2 or delta P is equal to 2S divided by R. So we have that particular equation, that is 2S divided by R. So we have one more relation, we'll mark it down as equation number 2. So again, if I rearrange this particular equation, P3 will be equal to P2 plus 2S divided by R. Just taking this P2 to the other side. So again, P3 is actually equal to P0 or simply P outside. So P outside will be equal to P2 plus 2S divided by R. So again, we have one more equation. So keep this in mind. Let's name it as equation number 3. Now what I'm going to do is that compare equation 3 with equation number 1, because on the left hand side both has PO, which is pressure outside. So we have two different equations but with the same left hand side, which means these two equations are comparable. That is, I can write P2 plus 2S by R is equal to P2 plus H rho G. So let's see what happens when I compare it side by side. So if I compare this equation, I have P2 plus H rho G is equal to 2S by R plus P2. So again, P2 and P2 can be cancelled and we have H rho G is equal to 2S divided by R. So what is so special about this particular equation? The speciality of this particular equation is that it gives us the height of this particular, or simply an equation in terms of height. So it is 2S by rho GR. So what is this R? This R is the radius of this particular bubble. So the radius of the bubble is indicated as r. It is an imaginary bubble. There is no bubble there, but we are imagining just for the mathematical sake of proving this particular equation. And what is h? Again, h is the height of the water column from the surface. So that particular height is indicated by h. So if water is sitting at a particular height and it is having an imaginary bubble on top with a radius of r, and rho is the density of that particular fluid, g is the acceleration due to gravity, and s is the surface tension, then keeping all that there, we can consider one more thing, and that is the contact angle. That is, I told you that there will be contact angle like this. So this will be the contact angle theta. So if this is the contact angle theta, then what will one more angle be? For that, we are taking a radius vector like this. So this is the radius vector like this. And from here, again, I'm drawing one more tangent like this. So what will this particular angle be? That will also be theta, because again, you have studied this in high school, you don't need the proof. If there is a right angle or simply 90 degrees between two angles, then we can say that this angle will be theta itself. That is, same angles will be there. And again, if this angle is theta, this angle will be theta. That is, same angles will exist. You don't have to know the proof or understand the proof. Just know that if this angle is theta, this angle will be theta. Okay, that is a mathematical proof which you have already studied in your high school. So for clarity purpose, I'll take that and put it right outside here so that you can understand that figure much better. So again, this would be radius vector r, and I'll name this as small r. So from this, what are we going to find out? Why did we do this? From this, we are going to find out what is that particular angle all about. For that, we are going to apply the trigonometric laws, or simply we are going to take cos theta, which is equal to adjacent side divided by hypotenuse. So what is adjacent side here? Adjacent side is r, and hypotenuse is also capital R. So r divided by capital R. So r divided by capital R will give you your cos theta. Now why did we just do this? We want an equation in terms of r, because here r is the radius of the imaginary bubble we have. So we cannot imagine a bubble every time like this. We need a mathematical proof. We need a tangible connection to this particular equation in terms of the actual liquid. So this particular small r will give us, or will form, a connection between the imaginary bubble we took and the actual situation there exists. So to form that mathematical connection, we are considering this particular trigonometric result. So again, we can say that r will be equal to small r divided by cos theta. So r will be equal to small r divided by cos theta. So we can substitute this in this particular result, which means that h is equal to 2s divided by rho g, and instead of r we can substitute this result, that is r divided by cos theta. So since it is in the very denominator, the leastmost part, it will go upwards. So we can write it as h is equal to 2s cos theta divided by rho g r. So this particular equation will help us to find what is the height of that particular water column. And again, with this, we finish the equation, or simply the derivation for capillary rise, and this entire chapter. So I hope you have understood everything about fluid mechanics, and the only thing we did was go in an examination point of view. And I hope you have understood everything. I'll see you all very soon with a new chapter. Until then, thank you.